Welcome to a journey through the fascinating world of nuclear fission. This transformative process, which involves splitting atomic nuclei to unleash immense energy, has profoundly shaped our scientific landscape. Join us as we explore its historical roots, the intricacies of the fission process, energy production, safety measures, and the often misunderstood realm of nuclear waste. Our story begins in the early 20th century amidst a flurry of groundbreaking discoveries in atomic physics. Ernest Rutherford and Niels Bohr paved the way, providing insights into the structure of the atom. Their work set the stage for the discovery of radioactive decay by Henri Becquerel, Marie Curie, Pierre Curie, and Rutherford. However, it was the neutron, discovered by James Chadwick in 1932, that opened the door to a new chapter. In Rome, Enrico Fermi and his colleagues bombarded uranium with neutrons, laying the groundwork for what would become nuclear fission. In 1933, physicist Leo Szilard formalized the concept that neutron-driven fission of heavy atoms could create a nuclear chain reaction. Finally, in December 1938, Lise Meitner and Otto Frisch deciphered that uranium nuclei undergoing fission produced isotopes of barium, unraveling the mystery. Nuclear fission, at its core, involves the splitting of atomic nuclei, resulting in the release of significant energy. In induced fission, a neutron collides with a target atomic nucleus, typically an isotope of uranium or plutonium found in nuclear reactors. The energy needed to initiate this process is around 7 to 8 million electron volts, MeV. Upon collision, the target nucleus deforms, resembling a double-lobed peanut. As the lobes separate, the strong nuclear force, which binds protons and neutrons, becomes insufficient to hold them together. The nucleus fractures into smaller fragments, releasing 2 or more neutrons. These liberated neutrons, traveling at incredible speeds, strike other nuclei, perpetuating a chain reaction. The energy release is a result of mass-energy equivalence, as per Einstein's iconic equation, EN_mc2. Even a minuscule difference in mass between the starting particle and its daughter particles translates into a substantial amount of energy. Not all neutrons produced in fission are available for further reactions, leading to potential challenges. To sustain a chain reaction, a critical mass must be maintained. Factors such as fissile material composition, density, purity, and physical shape play pivotal roles in achieving this critical mass. Spheres have been found to minimize neutron loss, and neutron reflectors can bounce stray neutrons back into the fissile material. Control rods, typically composed of boron or cadmium, act as neutron absorbers, enabling control over power levels in fission reactors. In essence, these safety mechanisms prevent the unbridled escalation of fission reactions. Understanding the intricate dance of neutrons is crucial in harnessing fission for energy. Neutrons created in fission are essential for driving further reactions, but their availability must be strictly controlled. Control rods, once again, play a pivotal role in managing power levels. Water infused with boron can serve as both a coolant and a neutron absorber. Delayed neutrons, emerging after fission, play a critical role in preventing uncontrolled chain reactions. Produced in small amounts with less energy than prompt neutrons, they provide a crucial element of control in reactor systems. In nuclear reactors, the capture of a neutron by uranium-235 often results in the creation of barium-144 and krypton-90, releasing substantial energy. This controlled process allows for the generation of electricity in nuclear power plants. The safety of nuclear fission has been a topic of concern since the dawn of the atomic age. Notable incidents, such as those at 3 Mile Island, Chernobyl, and Fukushima, have cast a shadow over public perception. However, it's essential to recognize the strides made in enhancing safety. In 2022, Our World in Data reported that for every terawatt-hour of energy generated by fission, there are only 0.07 deaths, in stark contrast to 32.7 deaths for the same amount of energy produced by fossil fuels. Fukushima, often synonymous with nuclear disaster, claimed 0 lives due to radioactive material leaks, as reported by the World Nuclear Association. Similarly, the 1979 Three Mile Island incident caused no deaths related to the release of radioactive gas. One persistent misconception surrounding nuclear fission is the notion of everlasting nuclear waste. Contrary to popular belief, fission reactors generate a relatively small amount of waste, with 90% falling into the low radioactivity category. High-level nuclear waste, constituting only 3%, releases 95% of the total radioactivity. Spent fuel, often misunderstood as a hazardous material, primarily consists of metal rods containing ceramic pellets of enriched uranium. Remarkably, spent nuclear fuel retains 90% of its potential energy even after being used in a reactor. Countries like France have embraced nuclear waste recycling, while the United States is exploring advanced reactor designs that could operate using spent fuel. Despite the challenges, responsible management and ongoing research offer solutions for the safe storage and disposal of fission byproducts. In conclusion, nuclear fission stands as a testament to humanity's ability to unlock and control the immense power concealed within the atom. From its accidental discovery to the controlled reactions powering our cities, the journey of nuclear fission is one of innovation and responsibility. As we continue to refine our understanding and technology, the promise of clean, efficient, and safe energy from nuclear fission remains a beacon for the future. Join me in future explorations as we unravel more mysteries at the intersection of science and discovery.